And Martin, whenever you're ready.
Yeah, let's do this. So today I'm going to present Semgrep. That's the polyglot static analysis tool that we've been developing at R2C. And here I am. So yeah, Martin, and my language of choice has been OCaml for 20 years now. Started in working on protein structure originally, and then for the last 10 years, I've been working only on, well, in startups in the Bay Area. That has nothing to do with biology, but yeah, that's my background, and our company R2C is based in San Francisco. Is focused on security. So the tool we're developing, even though I'm going to spend time on some internals that I'm more, how to say, an expert on. Yeah, the goal is just not just a toy, is to actually make something useful and prevent and catch bugs early, help developers not commit bad code by accident. So this is this aspect of security. So what is Semgrep? Starting about a year ago. Well, yeah, this company R2C is started. They developed Semgrep, which has a previous history at Facebook, and even before with Coccinelle, a tool that was developed in part with one of my colleagues, Johan. So he brought some of that expertise along. At Facebook, he developed parsers to parse PHP because they're using that at Facebook, and he added more languages. Then eventually he joined R2C, and I joined the Semgrep project last summer, and they are already getting started with this. They got good traction. People like it, and I'm going to present a bit how it works, and why it's appealing. So yeah, in short, it's Semgrep is a lightweight static analysis tool. It's really just like grep, but a grep that understands source code. So you write your patterns as code, pseudocode. It's really just really using the familiar syntax, and added to that, there are a few extra constructs for expressing patterns, but it's not very hard. So yeah, it's relatively fast also. And it works for a variety of languages. So that's going to be the focus of my talk today, how we deal with all those languages. So you can see the list here. Some are supported completely, others are still kind of in progress. And yeah, we'll come back to that. I present the tech behind that. So first, let me show you a bit of Semgrep. So, well, there's grep and there's trees. So what you can do with grep is, well, it starts easy. If you look at the first exec, well, you can catch that with grep. You have to put a backslash in front of your parenthesis, but other than that, it's going to work. Okay. Now third case, oh, there's a space before the parenthesis, so okay, we have to take care of that. So modify our pattern and add a backslash s for white space, and then oh wow, multi-line patterns. That gets really tricky with grep. Actually, I don't even know how to deal with that. And oh, a function is not really called exec, is something else underscore exec, and our grep pattern will probably match that, but we don't want that. And well, comments, well, grep is not going to understand comments. And same for string literals. All those things get really hard to deal with. So either you are too restrictive, or you have very complex patterns that are brittle, or you catch too many things which are false positives. So well, all right. So yeah, that's because Semgrep grep works on strings, and programs really are meant to be understood as trees. And that's the way we choose. So that's the correct way. You know, there are many tools that deal with trees for tree matching. There's a short list here. They're all specialized. That's the thing. They are specialized to one specific language. They will be good for certain types of linting or this or that, but not super generic. And yeah, we have to set up and learn a new tool for each of those languages. So that is difficult. Imagine if you are in charge of security at your company, you're going to want to review and audit all the code, and you may want to you want to catch certain patterns, certain bad usage, and you have to deal with all the languages that they use. Sometimes it's configuration files written in a special syntax, and all of these. Well, we want a way to find problems in those. So, and there are no tools for everything. So we're trying to give that. All right. So that's a blog about the two extremes, and we sit in the middle. So the regex-based approaches are, well, fast but limited, brittle, and on the other end of the spectrum, we have complex tools that can be slow or hard to set up. So yeah, we're trying to find this sweet spot where it's kind of, you can do the easiest things easily, the simple things easily, and also get some more advanced stuff done. So let me show you the basic usage of Semgrep. There's not much more than this, but the essential ones are this ellipsis and meta variable constructs. So let me start with the ellipsis. So we have this thing. It's a live editor. So let's go there. Okay, so this is semgrep.dev. You can find it. Semgrep, that's the playground that can be used to explore Semgrep and to create your own rules. So this is here a little exercise. So in this box here, with the to-do, this is where we're going to put our pattern. There are examples on the right of what type of patterns you want to create. You can create for Python here. This is Python. We could pick other languages, but this example is for Python. And here are some target program, which has a bunch of calls to exec, and we would like to catch those. Well, the correct ones. That is this one, obviously, line 4, line 6. Also, this one has space. We want to catch that, multi-line one. This one, we don't want to catch it. Also, the comment, that's a comment, shouldn't surface. This is a quoted string, it's not a call to a function. So the last 3 shouldn't match. So let's see if we can do something like that. So, well, this is our first Semgrep pattern that we enter here. Dot, 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 where we have a sequence of things. And let's see if it works. All right. So this is nice. We got all the calls that we wanted, even the first one, which is actually an alias. So other function, this other function is an alias for exec, and this was caught correctly. So this shows that, yeah, we try to do a little bit more than just syntax matching. And this is where the same means in Semgrep is for semantics. So we're trying to do a semantic grep. And so, yeah, we're progressively adding features to make it more and more powerful. Oops. Here we go. So the other special patterns we have are called meta variables. And a meta variable is like it's a capture, so we can capture things that match and give it a name. So here for this code, we're going to try to find places where we have something compared to the same thing. So something equals the same thing, whatever that is. So if you have here cat is cat equals cat equal to cat, well, okay, we want to catch that. We don't want to catch 7 equals 8. It's a simple example, which may or may not be useful in practice, but in general, you don't want to compare two identical things. So anyway, so let's try. So that's called this is the dollar. The dollar notation is special Semgrep syntax, and so we can do that $x. So if we do $y, that also means anything. X is anything, Y is anything, and this will catch anywhere where we apply the equality operator. So it catches everything. Now, if we want to catch something equals the same thing, all we have to do is use the same variable here. And ta-da. So yeah, it works. If you look here, we have the same exact expression on the left and on the right. Presumably it would be a programmer error. So we can make more complicated pattern than this, obviously. Yeah, so this is basic Semgrep usage. We offer other things, like I think one interesting one I'm gonna mention here is the fix. So Autofix. This example, we have highlighted a call to launch an HTTP server on port 80, whatever. But this uses this vanilla function that's insecure because it doesn't use TLS, and we want to find this one and replace it with the function that uses TLS. So this, in this view, we have the YAML config for the rule. It has a bit of fluff, which is actually useful. That explains the background, so that when the flaw is detected in the code, the user knows what's going on. But essentially, there's a pattern that we want to write and a fix for this pattern. So, all right. What is our pattern going to be? Okay, it's going to be http dot, well, this thing. And I don't really care. Do I care what's in here? Oh, yes, I do care what's in here because I'm going to reuse them. So, okay, I call this port. And here, what is this? Actually, I don't know. I'm going to call it X. And we want to replace it with the function called the same with the TLS suffix. Okay, so my fix is going to be this, and I hope it works. Okay, so we have a match. This is good, and a suggestion. Let's see if we can apply the fix. Ta-da! And the fix was applied. So that's an experimental feature, I think, in Semgrep. But yeah, we want that to work well eventually, because that's just nice. And so all the integration work of integrating Semgrep in CI is very significant. So I'm not really working on that. I'm going to present more the internals of parsing, but yeah, you get a sense of the sort of things we can do with Semgrep. And so now this was warm up, and you get a sense of what we want to do. So we saw that we deal with a bunch. We want to deal with various languages. Or maybe if I back up a bit, let me show you the languages that we have in there. So we have, those are listed here. So all those are normal languages that are programming languages. We have, I think we have JSON, which is just a subset of JavaScript. We have YAML, that's its own weird thing, but all the languages are managed in this similar way. And then there's this generic pattern matching, which is something else. I'm going to talk about it also. It's for dealing with unknown languages. But all the other languages are dealt with in the same fashion using the Semgrep pattern that we just saw. And so for that, we use this generic AST. So let's see. A pattern, as we saw, it looks like pseudocode. It's really it uses the same parser as the programs we want to match against the pattern. So it's just that the parser, the grammar for the parser is extended with ... and meta variables, but they use the same parser, which is interesting. And they both result in some AST, and we call that the generic AST. That is, regardless of the language we start with, which is in this example here, we have Python, Ruby, and JavaScript. We use one technique or another to get to our generic AST, but they all converge to this generic AST, and which is a uniform representation that accommodates all the languages. And that's quite nice. So here we have three parsing flows, but the main one is the one we prefer now is using tree-sitter. I'm going to explain a bit what tree-sitter is. And it goes in two steps. And the first step is, well, we have a whole machinery that gives us a CST, concrete syntax tree, also known as the parse tree, which has all the details. So all the semicolons, parens, and so on. Whereas an AST might strip these off and it is nicer to work with. So from tree-sitter, we get a CST, and then the CST is adapted, is mapped into the generic AST. So I'm going to show a bit of that. We also have legacy parsers. The ones we came with the that Johan developed at Facebook. So Python, for example, uses this parser. It's actually written using Menier, which is parser generator for OCaml. There's nothing really special about it. It works well, but these parsers need to be maintained. On the right, we have another flow that's more complicated for historical reasons, also based on tree-sitter and some also on the old stuff. So I'm going to mostly show you the tree-sitter stuff today. So yeah. So anyway, once we have when we have a generic AST for our pattern and for our target program, we can compare them. And this is what our matching does. So we have a single, well, pretty consequential piece of code, but a single piece of code that takes care of matching a pattern against a target program. And this all works on our generic AST. See, I can show you the proof here. Earlier, I ran our parsers on on a Python program on the left and a JavaScript program on the right. They are really simple, and you can see a dump of the generic AST. So if you look close, you'll see that they are the same. We have a function definition in both cases, and everything is very similar. There's no notion, there's no clue that we're using Python or JavaScript in these ASTs. On the right, we have console.log instead of print, so that makes a difference in the tree. This is the beast. This is our generic AST, and as you can imagine, since we accommodate all the languages, and each language has its own set of features. We have many nodes, many kinds of nodes in our tree. So this is a snapshot. I could show you more details about this tree. It's not that interesting, but it's about 2,000 lines of type definitions. And for those interested, we started an effort to make those, to export the AST in a JSON format that will be documented and usable from other languages. You can ask me about that if you're interested, but yeah, we think it could be useful for others who like to experiment on, doing stuff with programs and doing so for multiple languages, not just one. This huge AST needs to be traversed when we do several things, different operations. One of the big operations is matching, but we do other things, constant propagation and optimizations and this and that. And we can't really have 1,000 lines of pattern matching each time if we want to just scan the tree for something. So here's a little example. I took this snippet of code from an optimization that we do that needed to access, to visit statement nodes and identifier nodes, but it doesn't care about the rest. So if you look at the k ident identifier here, that's a field in an OCaml record. So if you're familiar with the visitor pattern, that's great. Otherwise, yeah, I'm going to explain it. So what it does is there is a generic a function that's written once and for all that will visit all the nodes and all the kinds of nodes in the tree. And when it finds a node of type, in this case, ident, it will call the function that we provided that is in charge of doing something with that node. This is the little anonymous function we have here, which does something with this ID. If you the next one, the other one is STMT, that gets called when we visit a statement. Also, we do something for a statement. This machinery works. It's typically used in other languages than OCaml that don't have pattern matching and they don't have algebraic data types. In OCaml, we have those. So this is feels like a step, I don't know, it feels a bit heavy, but it works. And well, if you need to visit like just the identifiers, for example, in your AST, it gets the job done really fast instead of writing 1,000 lines of recursive functions for dealing with all the possible cases. So that's how it works. Yeah.
I have a quick question.
So
your generic AST, does that carry enough information to do like translation between languages, or Or is it short of that?
So you saw the Autofix. I showed the Autofix example. So we do indeed. I haven't worked on that myself, so I don't know how well it works. We have some way of printing back into a concrete syntax for a specific language. I don't know how well it works or if it works for all languages, but yeah. So in that sense, there would be a way to go from concrete syntax to generic, and then pretty print that generic snippet into a chosen language that would do a translation. Yeah, we'll have to look at the quality of this transformation, but yes, at least some of it is supported. Yeah.
Thank you.
And yeah. So once we have this generic AST, we're good to go. Basically, that's my message here. There's a lot of possibilities that are offered. We don't need to worry about specificity of, well, there are still specific features of some languages that are present in this tree, but we could also choose to not deal with them depending on what we're trying to do. If we just want to find function calls, like don't need to know about all the features of our languages. You can do
I would imagine trying to make something that also understands like Rust borrow checker or something like that would be
yeah. So yeah, so we're gonna have some Rust specific node in our tree. We have this for many languages. Sometimes there are some kinds of nodes that are specific for one language, like OCaml, for example. It's functional, so it doesn't have state. Well, I mean, it doesn't have state. Things are organized a bit differently. So, but it works in the end. Yeah. So that's nice when we get to the generic case. That's my message. Getting there though is interesting part I'm gonna talk about now, like the various parsing technologies. So let's see. I mentioned tree setter earlier. I'm gonna talk about more about that. But the main two parser generators we're using now are Menier, which is an LR1 parser generator for OCaml. LR1 is a type of grammar, if you know or remember this. One means this allows the parser to choose which branch to take based on the looking ahead the next token. And most of the time is good enough, but not all programming languages are designed to work like that. So sometimes it's harder. And actually, this other tool, tree setter, lets us do that. I'm gonna explain a bit more. So we use those two. So we migrated to tree setter last summer, and that's big interesting thing. We also have a handwritten OCaml parsers when they're available. Like for YAML, we added YAML recently. We just use the YAML library for OCaml, and that's great. It's it's not very simple language actually. So we're happy to use library. And I'm also talking about something I developed, which is this catch-all fallback. It's called Spacegrep, which is a step below Semgrep, but it's more in the spirit of Semgrep. So it's kind of between the grep and Semgrep, hence the shared grep suffix. All right, so let me show you a bit about tree setter. Tree setter is a big project that was created by Max Brunsfeld, who was working on it recently at GitHub. GitHub manages this project now, and it's open source. So everyone benefits. It was designed specifically for editors, so it supports incremental parsing. That's not something we use for purposes, but okay. What does it do? Well, it's a parser generator. It generates C code. That's nice. At least for us from OCaml, we can call the C code and get the parse tree. Great thing is that there are grammars for this. Many of them were developed by Max, but now there's a bunch of community members, including ourselves, contributing to those. So yeah, there are grammars for many languages, like maybe, I don't know, how many is it? Something like 30 of the most popular languages. It's increasing slowly. So why did we use? Why are we using tree-sitter? Well, it was a very rational, well-considered choice. Problem is that maintaining grammars in OCaml for many languages is a lot of work, not because of OCaml, but because we are on our own. So instead, tree-sitter has many contributors. So the community will contribute to the grammars. We also contribute to the grammars. Everyone is happy to benefit from each other's work, and it's a lot more productive because indeed writing the grammars is time intensive, and yeah, not always obvious. So that said, tree-sitter has some unique features as well that we take advantage of. So one of them is GLR parsing. So GLR stands for generalized LR. And so if you worked with parser generators like YAC, sometimes you get static conflicts. So at the time of processing the grammar, YAC will tell you, oh, you have a conflict between this and this. I don't know what to choose. And you have to pass to specify precedences. And great. And if you're able to do that and determine statically what rule or what branch should be picked, that's great. But sometimes it's not possible. And this can be very tricky. So instead of doing some weird pre-processing work, there's this dynamic conflict resolution in which the parser will try all the possible branches. And if one branch works and the other ones fail, that's great. We take the one that works. If several succeed, there's a system of scores, and the ones with the highest score will be picked. So it's a very nice way of getting out of difficult parsing situations, and it's optional. It has to be specified in the grammar, so that's also nice. So it's not the default because it's a little slow and you try to avoid it, but it's really just one option that we have to make to solve difficult problems. So that's very nice. The other one is error recovery. So error recovery, when the parser finds the region of the program that can be parsed, but it can be skipped over, then it does this. So we get, in our parse tree, we see an error node somewhere. We can happily ignore it, and the rest of the AST is, or the CST, the rest of the tree is still valid and well formed after removing this error node, and that's really cool because, well, if you're in a text editor, that's a benefit because you want most of your program to be syntax highlighted, and what you're typing is not highlighted, but that's okay. You know it's broken. So this is good for this situation. In Semgrep is great because sometimes some new syntax is not supported by our parser, or it can be that there's a programming error, you know, that happens. But most of the time is that we don't support a specific syntax feature, maybe because it's too recent. And we are still able usually to parse most of the file and ignore the line or the few lines that have the error. And that's really nice. So this way Semgrep can scan most of the code, 99.99% of the code if we have good grammar, and just one line here and there will fail. So those are the good things about TreeSitter. So this is, I don't know if I should really go into the details, but this is a TreeSitter integration work we had to go through to make it work with OCaml. There are multiple steps. The first step is, well, natural. We have to add, since we're going to pass Semgrep patterns with the parser, we need to support ... and meta variables, and we extend the grammar for that. That's fine. Then we have a step of code generation that produces a grammar in JSON format. That's very nice to deal with. We simplify it to make it easier to process for our code generator. We feed it again to TreeSitter that produces the final parser.c. That's usually 100 or 200,000 lines of C code. And this is the parser that's going to run, and we're going to be linked to OCaml code. But our code generator then takes the grammar.json and generates several files. And some of this is a little tricky, but yeah, we generate one type for the concrete syntax tree that is completely very nice to use in OCaml. We have a file that does some recovery code because the tree we get from TreeSitter doesn't have all the information, so we have to recover some information to match to know exactly what branch in the grammar was taken. That's a little tricky. I'm going to show something, but don't panic. And there's also a big boilerplate file that's involved in mapping our CST to the generic AST. So some of that boilerplate is generated and the rest will be done by hand. So let's first look into nice and clean things that we do as they were intended. So here is a little grammar extension. The language is Kotlin. That's one of the hot languages we are in the process of adding support for. So this here on the right, we have a full grammar extension that starts from the official TreeSitter grammar for Kotlin. And this is JavaScript. So it's a whole DSL within JavaScript, so a domain-specific language that is used for specifying our grammars. It's pretty nice, given that it's plain JavaScript. There's a choice function, for example. In here, the expression, so expression is a rule, a grammar rule. And here we say that the previous grammar rule, previous, is going to be extended. So it's a choice to which we add other choices. So sorry, previous is some rule, and we turn the expression into a choice between whatever we had previously and these new constructs. So $.ellipsis is our ... and this is another one that I didn't present. We also have something from meta variables. So this is how Tricitor grammars are written. So the original grammar, if we look into it, it's just like this, but it's like 1,000 or 2,000 lines of similar code, of code like that. And now you can see that here we have this choice operation between different rules. This ellipsis rule and this deep ellipsis rule, and previous, we don't even, it's not clear what it is, but it's whatever it's a previous value for the expression rule. The choice, so this choice is an alternation, and each of the choices will be translated in our AST into a case, so into a kind of node, because an ellipsis is one kind of node. The previous expression, whatever it was, it's another kind of node. A deep ellipsis is another kind of node. And we want that to be well typed in OCaml. So we have some machinery to make sure this happens. And this is a bit of what I'm showing here. So if we run the Tricitor parser using the Tricitor tools for this simple Hello program, here's what we get. This function definition gets translated into this thing, which looks very neat and concise and has nodes that make sense. Now the problem is it doesn't show us everything, unfortunately, and we have to recover certain parts. So on the left, that's I highlighted a region where Tricitor, the original Tricitor output shows an expression statement, and this expression statement has a child that's a call expression. Very nice, you might say, but if you look at the grammar, the path taken is more complicated, and we actually want all that path. So if you look here in this recovered CST that we have in OCaml, we have new nodes here. So the first one, exp stmt, that's one kind of node that's the expression statement. And there's the call exp that correspond to call expression on the left, but in between there are two sub levels that were completely omitted in the original output. So yeah, we have a machinery to recover that, but takeaway is yes, it works, and it was quite an adventure to get that to work. But anyway, we got some good generated OCaml code, so I'm going to jump to that. If you have questions about this stuff, we can talk about it later. So the generated code looks like this on the right. We include the original grammar for reference. That's useful because it's the most readable version of the grammar. Everything that's derived from it gets less and less readable. The other thing is that it's a Dune ready project. So Dune is the build system for OCaml. It's completely how do you say, modular. So you can plug this specific repo. You can take this Git repo, plug it into as a Git sub module into your project, and if it's already a part of a Dune project, Dune will find it and will build all of this very nicely. So thank you thank you to Dune people for the great tooling. It works really well, and that makes it easy for us and for users of OCaml. Let me show you a bit of the generated code. Okay, so this is for Ruby. We generate one Git repository for each language, because it's convenient. We like to work on on languages independently. So anyway, this is a large amount of generated code. This parser.c, that's the main thing that TreeSetter generates. I think we can't open it because it's too big. It's in the hundreds of thousands of lines of C code. And we have our OCaml code, in particular this one that is in charge of doing this recovery I alluded to. This is part of the machinery. It's all nicely pretty printed. If you know what's going on here, you can recognize a language like alternative sequence. Those are essentially regular expressions, and we run regular expressions on the children to figure out the kind of the different children we have in our original CST from TreeSetter. And the regex matching allows us to match those children with the anonymous grammar rule, and then we can name every piece. It's not supposed to make sense, but I like to watch that generated code. Is always so satisfying. And it's pretty long, so I always feel good about this because I just don't have to write that or even worry about that or even open it ever, because it's pretty mechanical. It's debugged really when you write the generator once and for all, but then it just works. It's cool. Now this CST.ml, that's what we're going to consult as a reader and a programmer, because we're going to have to do some work on the CST to convert it to the generic AST. So the CST type that's generated by our tool, OCaml TreeSetter, and all those types were generated from the grammar. So this is a mirror of the structure of the grammar, and everywhere we have a choice in the grammar, which is an alternation between different rules. This results in an algebraic data type. So this one is, well, it's almost an enum, but yeah, each of the possible cases receives a name. Here we get cute names based on the actual ASCII characters involved. Sometimes it's less, sometimes you're trying to give good names based on what we see. You need to give good names that are, meaningful to a human, and that are also, how to say, non-conflicting and stable. So there's a whole art of naming things. That's one of the 2 or 3 difficult problems in computer science. So yeah, here we go. Sometimes we have things that are named less nicely, like this. Oh, here's one. This one was called Anon Choice CST, some hash. That's the best we can do because it's inline patterns, inline things that don't really have a good name. And also that's the name that we generated. So anyway, so this whole thing is for is the concrete syntax tree definition for Ruby, the Ruby language, and I think the grammar is about 1,000 lines, and this one, this generated file is 1,200. Yeah. So let me go back to the slides. So now, okay, so with TreeSetter, we get a very nice CST via some OCaml transformation. And the thing is, the CST is very specific to the language we are parsing. So we only need to translate the CST to the generic AST. You might think, that may be a lot of work, and why didn't we write the grammar by hand? Well, writing a grammar is the most time consuming operation here, because yeah, converting the CST to the AST is some manual labor, but it's not that hard, especially once you know the generic AST, what construct it has. It's not that hard, so we still prefer to do that. So yes, we're doing this crazy operation of starting from this generated boilerplate, which is a function that maps. So here's just one example. We have this map argument list. So argument list is a type of node, and this defines a function that maps an argument list node into something else. And this something else should be something equivalent in the generic AST. So what we could generate is this boilerplate with to do. So we have to do here, to do there, and that will have to be replaced by constructs of the generic AST. So that's the labor-intensive part. And so by generating this file already automatically, we get half of the work done roughly. I can show you the original generated file. So the generated file looks like this, and this is our boilerplate, generated boilerplate. It wouldn't be fun to write by hand. It's structured in a somewhat obvious and repetitive fashion, so that's nice. Now we map this by hand, and then we have to maintain that. But this is the hand modified version. So we replace all the to-dos with actual constructs. And what can I say? Yeah, for example, here there was a to-do originally. Now it's an empty list. So we have something that a list of parameters or something here. And yeah. And so we have to maintain this mapper. Again, this is pretty long, but it's not that hard. All right. And so that's all for the Tricetus stuff. Hope I give you a good overview of how we do things, that it's not that simple. There's a lot of code generation passes, and it's very satisfying in the end because we feel very, powerful. We can deal with all those languages at once, and they all converge to one way of doing things. Now, the other thing I mentioned earlier is, well, what if we have a configuration file for, I think Terraform has their own syntax for config files. We have maybe exotic languages that are used here and there in some code base. Or maybe we want to match some HTML snippet that's embedded in some special templating language. And well, we do support JSX, and which is a React extension for JavaScript, but maybe we don't support this specific templating mechanism or whatever. So for those, we have this Spacegrep tool, which is our last resort. And so we didn't want to. I thought it was too bad to not be able to use something like Semgrep when you don't have a grammar and have to resort to grep, and grep being so unaware that things can be on multiple lines. It was frustrating. So this Spacegrep tries to do things like Semgrep when possible. It should be usable by a user out of the box. No configuration needed. They write pattern that looks like the actual code they want to match. We don't need backslashes. Oh, I think that's very pleasant. And yeah, it's just easier than grep. It's kind of like some grep, but not completely. So let me show you what what we can get out of it. That's a screenshot of what we get. Let me show you in the live editor. It's loading. So I entered this exec pattern we had earlier. Here you can see the language chosen is generic. Actually, you might be able to run this same exact thing with Python. All right, so with we don't catch the notion that there's an alias. That save function is the same as exec. Spacegrep has no idea. It has no idea about, well, it has idea about identifiers. It didn't match this one. That's nice. Multiple lines are not a problem. And what else? It doesn't know about comments. Doesn't know about string literals even. Now we can still do certain things, like see, for example, if we want to match anything that's in the string, that works. That should match only this one. Yeah, this is correct. Maybe we can do something like that. Maybe we want to catch all the exec, but exclude those that use a constant string as argument, because that's considered safe. You don't want to execute arbitrary code, but executing a hard-coded command, that's perfectly fine. So let me try this. So this should match the dangerous execs, and so yeah, we can do that here. So we didn't catch exec ls because this is secure, whereas some var, we're not sure where some var comes, and that could be dangerous. If you compare to Python, actually this syntax can be used also on Python, I think. Let's try it. It's a live demo, but yes. So Python works better. That's the regular Semgrep that has notion of comments and strings. But other than that, yeah. So you can see that the generic mode is limited, but for simple things, it's gonna work, and we might get false positives, and well, that's okay. But yeah, so that's the thing we have. So how does it work? Well, I think I wanted to show you a bit of the OCaml code involved, because it's so much simpler than the full-fledged generic AST. So the view of the program is really simple. A program is made of atoms that are one of those three things. It's a word, a punctuation, or a byte, and a node in our AST, well, AST or CST for Spacegrep is a list of nodes or an atom, and this is all the definitions we have. On the right, we have the tree corresponding so the AST definition for a pattern, and you can see that we have these extra constructs, so for meta variables and dots. And yeah, we do support some meta variable matching in Spacegrep. And yeah, that's simple and nice idiomatic OCaml. Same for matching. So for matching a pattern against a tree, that's very idiomatic OCaml. I think I'm just proud of this code, so I wanted to show it here. Like, that's the kind of the way of writing OCaml code that's nice, and like we learn in school. That's it's not too complicated. Once you understand how to write recursive functions to deal with trees, and you get the notion of pattern matching, that should be understandable. That's I think that's all for Spacegrep. So I'm going to conclude my talk here. And yeah, so this is our program analysis team with managers. 4 people, Emma, Iago, Johan, and myself are working on the core of Semgrep and making it better every day. Thank you all for your attention. So if you want to install it, you have instructions here. You can find them online. We have this online editor, the Playground, that I use for the demos, and you can play with that. Feel free to reach out on Twitter or to me directly, and the little survey here if you're interested. And that's it. That's all for my presentation. So let me know if you have questions, if you're inspired or terrified by this.
Definitely the former. This is pretty great. So how incorporated has Semgrep become into your development process?
Into ours, well, we use it on our source code, you know, dog fooding. We don't do very much with it. I think it's very valuable for, we're doing static analysis. So even though we run it on OCaml, we don't find that much stuff. It's really, I think, it's going to be useful for like real, like to say applications, web applications that involve have a lot of IOs, especially user input, tainted input. There's a lot of security issues there. So yeah, we haven't. I myself as OCaml, someone involved with OCaml, didn't have to fix many errors. When I touch on Python code, something surfaces up sometimes, and yeah, yeah, it's nice. We are not submerged by false positives as far as I can tell, which is good. Yeah. If you want a perspective on security issues, I think we have talks by our colleagues. I think we have Clint Gibler gave something that's available online. I can give you a link. I think I posted on Twitter earlier, where he goes more into details about real world usage. Yeah. Did I answer your question?
I suppose you did. You use it occasionally, but it's
Yeah.
if you're writing OCaml, then everything's
Yeah, that's the thing. It's a little weird. So this is a functional programmers group. So I'm gonna say things that should sound familiar to functional programmers, but it's like a kind of a niche. I mean, at least OCaml is not extreme widely used, and we use it especially here for the kind of things where it shines really. That's so we are kind of in our little world. Yeah. What can I say? Yeah, I lost my train of thoughts. I kind of want to repeat. I don't want to repeat things, but yeah.
I did have a question. So like what kind of, do you see any applications to like editor tooling? I mean, I noticed that there's a Semgrep plugin for VS Code, but have you seen like a lot of use there? It seems like it'd be really powerful in.
Yes, it is. So we have excellent colleagues who take care of that. I haven't really followed myself. And yeah, there's a lot of stuff to do there. I think there's some VS Code plugin. Not sure about other editors, but yeah, that should run in the background. And as you write code, it should find problems. So the integration is indeed a big effort. A lot of work to be done there, to be, have things up and running quickly in CI, and that should run fast enough also. So speed is more on our side. make sure things are fast enough. So that's an issue, but there's also convenience. We want to make sure that things are reported correctly and are easy to fix and not surprising. So we have these rules, these rule sets, so libraries of a library of rules that are made over time by some of us, also some external contributors, and for catching problems. A rule is a Semgrep pattern usually, but at least usually there are several patterns, to make things, to capture more interesting things, and a message explaining what's going on. There's possibly a fix, like I showed earlier. And so all these rules, I think we have over 1,000 rules now in Semgrep, and people can use these rule sets. That's the config shown here on this slide, R2C. That's one of the rule sets, I think, and it's meant to be easy to use in practice without having to create your own rules. However, you can make your own rules if you have specific code that's a little dangerous and you don't want your users to call it. Then, well, sure, you can make your own rules. Yeah. Yeah. So yeah, don't hesitate to ask more, or then let me know if I didn't answer your question. Does anyone else have questions, or do you guys know about OCaml a bit, or I'm not sure about the background of the audience, or were you? Yes.
There are a few ML line language users here. John, Mr. Bremer, myself to a small degree use F#, and then Claude is mostly focused on OCaml, and I believe there's some other OCaml users in this group as well.
Yeah. And yeah, if you have comments on OCaml, is there anything you find strange about what we're doing? Let me know. I know I've been in different teams over the years. There are different ways different types of applications are being done with OCaml. I know that at some point I was in a web startup, so we're doing we had the whole backend that was written in OCaml. So then with that, we were using LWT, and the big thing. So we had an HTTP server, and a lot of JSON was involved, and that's very different from what we're doing right now. Yeah, different people also prefer different styles. Well, this would be strange to not like it, but I really like our style right now, which is kind of, we try to keep things plain and simple. Like OCaml has advanced features that has modules, or the module system of OCaml, a module, and there are modules and functors. So functors is a parameterized module, and now they are, so we can parameterize a module with types or with data. And you can have also now, in recent versions of OCaml, we can have first-class modules that can pass around, and you have to unpack them. So use them. Sometimes they are viewed as module or viewed as values, and there are ways to convert those. And I know some people love that, and I know I don't know. I don't know how to use that really well. So we try to keep things simple. I guess that's the style that we have here. I don't know. Yeah.
So do you find yourself using, for example, in situations where a library version changes and the surface area, the interface changes to that library, do you find yourself using this to do, updates to code bases using this tool?
using using Semgrep. How would you?
There was a syntax using replace there.
Yes. Yeah.
So you could define one pattern and define the other pattern, and then
Could I jump in with a concrete example? I'm thinking like maybe going from like Python 2 to Python 3 or something like that. Is that kind of what you're thinking? Like, or
yeah, or the module that, or the library that supports HTTP requests had its interface changed between this this version of the library and the some later version of the library, and just doing that kind of syntax transformation within the same language, of course, but with modifying to support the a named function, for example.
Yeah, so sort of thing that should be possible. It's I don't know if in practice that's something that works really well. I mean, I kind of imagine that APIs change because they don't change in a one-to-one way. Like it's not just a name that changes and keeps the same exact meaning. If they change the name of something, it's because maybe it's different. I'm trying to imagine. Sorry, I'm just speculating. Yeah, but I think it's a valid question and application. And so Coccinelle is the tool that Johan was working on originally in France, and they are focused on C, and they have a way of searching for code and patching it automatically. And this stuff is used. So yeah, it's used on the Linux kernel, and yeah, it's good stuff, but it works only for C. And yeah, so
I seem to remember some other projects based on, or there was a company being built off of Tree Sitter that was doing some of the things like that, but that was that's not open source, right? So I was just curious if Semgrep could be kind of used in those scenarios.
Yeah. I mean, yeah, you can use Semgrep for various things. Yeah, I think that the focus is really, I mean, it's a startup. Things change really fast also, and I don't speak for all for the rest of the company. Because I'm really focused on the internals. So yeah, I don't want to say something stupid, but yeah, it's always customer first. Get to make things that are that are in a heavy demand. So I would say it's security focused, and trying to overall we're not how to say. It's not like dynamic analysis where you would try to crash a system. Here we are more about helping developers avoid to not write bad things by accident. But yeah, the general, how to say, vibe that I get is like, yeah, we want to help developers first, to not have tools that get in their way. We don't want the security hat person to impose tools to the developers that the developers will reluctantly use. So yeah. So yeah, that's what we're trying to do. I want to say, yeah. Sure, I kind of digressed a bit, but yeah.
That's kind of what we do anyway. We our meetings usually end in massive digressions into interesting subjects. So welcome to the Houston Functional Programming Users Group.
Yeah. It's a startup. Things move fast, and that's that's nice. I can talk about other things. I don't know if you have questions about the company. Or yeah, anything. Or if we are done, I don't know. It's fine, but let me know how many people we have. I don't have the full view of the audience. Is it? Yeah. What do you think, David? Should we stop here, or are there more stuff we want to discuss? Or